Okay, welcome to Part B of the discussion on quantitative structure-activity relationships for the Medicinal Chemistry NCSSM online program. As we've talked about a little bit in the first part of this conversation, what you're trying to do in QSAR are find one or more descriptors or parameters that we can use mathematically to predict some biological activity, at least in terms of medicinal chemistry. We're trying to predict a biological activity, such as a drug's ability to cure some particular disease. And again, most of this is done using computational chemistry, so there are a variety of descriptors that we can choose, and descriptors defined as one or more things that explain some property in a group of analogs or related compounds. Okay, so that's basically what a descriptor is. So there are a number of things, and you've experienced some of these already in some of the previous labs. So there are some descriptors we call constitutional, such as molecular weight, the number of rings, the number of hydrogen atoms, the number of non-hydrogen atoms or heteroatoms, the type and number of functional groups would all be examples of constitutional descriptors. There's also, as I think we've mentioned earlier, topological or connectivity indices, which we're not going to spend any time with in this particular course. There are some electrostatic descriptors, and many of these come from computational chemistry, such as the ability to form a polar molecule, whether or not the molecule has a dipole moment or is a polar molecule or not. These will all be examples of electrostatic descriptors. There's geometrical descriptors, such as the volume of the molecule, the surface area of the molecule, the shape of the molecule, what we call shape indices. And there are some statistical mechanical descriptors, such as the vibrational frequencies of a particular molecule. Okay, so those are all molecular descriptors that we can use to as parameters for using to predict the biological behavior of some particular compound. There's also a number of quantum descriptors, and these are certainly easier to determine than experimental descriptors. Those of you who took computational chemistry understand this. You were able to build molecules and run a number of computational calculations that would give you a number, and getting that same number or getting a related number in the lab requires a lot more time and effort and expense. Okay, so things like atomic charges, the frontier orbital densities, the HOMO or LUMO values, the molecular orbital energies, again, HOMO or LUMO, these are all examples of quantum chemical descriptors. We didn't talk about this in the Comp Chem course, things like susceptibilities and super delocalizabilities. Say that word fast 3 times, okay? Looking at, for example, nucleophilic, or electrophilic, and radical susceptibilities. Again, not a topic we covered in the Comp Chem course. Atom-atom polarizabilities, molecular polarizabilities. We did look at dipole moments. We didn't look at any higher order of moments, but we looked at dipole moments. Again, looking to see whether a molecule is polar or not, and looking at the total energy of the molecule. These are all values that we can determine computationally using computational chemistry software like Gaussian and MOPAC and some of the tools that at least some of you used in the computational chemistry course. Okay, and quantum mechanical calculations, or QM calculations, are really pretty attractive as a new source of descriptors. And most researchers are including these descriptors because they're easily calculated. We don't have to measure them in the lab. Okay, there are errors that we get from this because of the approximations we make, but for all intents and purposes, the errors tend to cancel out since the errors are transferable or the same in structurally similar molecules. So if I'm comparing apples to apples, the errors will cancel out. If I am trying to compare one type of chemical to a very different type of chemical, then the errors are important, and I have to pay attention to them. Okay, and you should also understand that QSAR is certainly an aid to help us make some sense out of which molecules do we want to continue to explore in terms of their ability to serve as a drug, but none of that can substitute for chemical intuition or experience. There are times when the mathematics will say that a particular drug has a high potential to be a successful drug that will cure the disease and make the inventor rich. But sometimes the mathematics has to be taken with a grain of salt, and it takes a little chemical intuition and some experience to be able to say, well, I know what the math is telling me, but I still don't think this drug is going to be a commercial success. Okay. Um, as before, structures with certain functional groups are not good drug candidates, and you've seen a little bit of that already, and we'll spend a little bit more time exploring which functional groups are good and which functional groups are probably not good for drug candidates. Okay, you should understand that QSAR or QSPR is a statistical technique. It primarily uses linear regressions or regression methods. You know regression methods as y equals mx plus b, but there's certainly many more complicated types of regression methods. There it is, where y is the thing being calculated, m is the slope, x is the descriptor, and b is an intercept. Okay, there are polynomial regression methods. So here's a multiple regression method where you notice I have, in this case, I have three descriptors. I have x1, x2, and x3, okay, as all being very different descriptors, okay? And basically I'm trying to come up with, predict whether or not there's a goodness of fit between these parameters. Does this regression equation is it statistically significant in terms of being able to predict whatever it is I'm trying to predict? Okay, there's a very specific recipe or algorithm known as the Hansch algorithm. Corey Hansch developed this in the late 60s or so. And fundamentally what the Hansch algorithm is doing is looking at log p, or the partition coefficient. And sometimes you'll see it as written as log p OW. That stands for octanol and water. Octanol is a alcohol that we use to measure experimentally the log p values. And basically it's looking at log p's, as you should know by now, are looking at hydrophobicity. I think I've been using the term lipophilicity most of the time, how lipophilic is the drug, and that's a equivalent of hydrophobic. Okay, and basically this is a measure of its ability to pass through a cell membrane. So you should know by now that if something has a high log P, it has a pretty good ability to pass through a cell membrane. Okay, and what we do here experimentally is we measure the relative solubility of a drug in octanol, which represents the lipid bilayer, and water, which represents the fluid within a cell and in the blood. So log P values can be measured experimentally. We do that all the time. But they can also be calculated, and this is what we do mostly in this course, is we try to calculate these log P values so we don't have to measure them experimentally. Okay, so here's an example of calculating a log P, and there's a couple ways to do it, and we'll show you one way here. Okay, so log P is the same as the log K of this octanol water mixture. So you see there I take the log of the concentration of whatever X is in octanol divided by the concentration of X in water. And that's sort of the framework for how I get this value. But one approach is using what's called a group additivity approach. So for example, I can say an aromatic ring, that benzene ring there, has a log P value of 0.780. I can say, okay, there are now 7 hydrogens that are connected to a carbon. We don't see the hydrogens here, but they're there. And that has a calculated value of 1.5891. I can say that the carbon-bromine bond is a negative 0.120 in terms of its addition to calculating log P. I can see there's one alkyl carbon there, and that has a value of 0.195. And if I add those all up, okay, that adds up to 2.924, and I would call that the calculated log P, sometimes known as the C log P. You've seen C log P on the drug design tool that we used a couple weeks ago. So this is the group additivity approach where Hansch and others have gone and they've calculated how much each of these parts of this molecule are worth, and to predict the log P it simply adds them all up. And again, that's what the software did. The drug design tool, again, that we used a couple of weeks ago, you clicked in different things into your molecule with the builder, and every time you added something it either added or subtracted some amount to give you a calculated log P. Okay. And there's certainly, this is a very simple or actually simplistic approach. There are many more complicated algorithms, in fact, including factors such as dipole moment, molecular size, and shape. So there's lots of ways of computationally or mathematically figuring out the log P, so we don't have to do this experimentally. Okay, Hansch's approach was a little different. Okay, he did use some of the additivity methods, but he came up with what's called a substituent constant represented by the Greek symbol sigma, seen in the parentheses there. And basically, this is a measure of the molecule's intrinsic reactivity. And what he was particularly interested in were the electronic factors. Okay, can he measure? Okay, what he tried to do is measure the influence of where the electrons are in the molecule, and tried to figure out, can he calculate some of these factors, how electrons are distributed throughout the molecule. And so what he figured is substituting something on an aromatic ring or a benzene ring would alter the rate of a reaction. And he came up with some number of orders of magnitude. So as a quick example, if you look at the thing, the molecule down below, okay, and see where X is, if I make X a methyl group, then this reaction that you see at the bottom of the screen will proceed sort of at a normal speed. Okay, so what you see here is I'm taking this substituted benzene ring and has a chlorine attached to a carbon and all that stuff, and I'm reacting it with some methyl alcohol, and what I get on the other side is now I get an ether on the other side. The chlorine has been displaced, and now it forms a hydrochloric acid. But this reaction would happen at a normal speed. Well, what if I change the value of X? What if I change what X is? Okay, so if I make X a nitro group or an NO2 group, that will make this reaction happen 100,000 times slower. So Hansch was able to painstakingly measure all of these substituents, so changing what X is, and he was able to measure how much each of these things that we substitute onto the aromatic ring were worth. Okay. And so as an example, and you did this as a lab a week or so ago, the substituted benzoic acid. So in this case, you see the substituted benzoic acid before where I have an R group, okay, or something attached to the benzene ring. Okay, and I react it, and what I get on the right-hand side is the carboxylate anion. You see that thing with a minus charge on it, and I get that should be actually a hydronium ion there. That should be H3O plus there. Okay, and so what happens here is if R is electron donating, okay, and you can read about that in your book a little bit. It's also what we did in the lab last week. Okay, then the acid form is stabilized. It's going to be more acidic. Okay, and the equilibrium, equilibrium goes to the right. Okay, if if R is electron withdrawing, that stabilizes the right-hand side of this reaction. Equilibrium goes to the right, and I have a stronger acid. So Hansch also looked at substituting on things like benzoic acids, and he was able to figure out some of the properties of electron donating, electron withdrawing. Okay, and it's a hard concept, and many of you are probably still struggling with it, but we'll continue to work with it, and it'll get easier as we go, as you get a little bit more experience. Okay, so Hansch primarily was looking at the influence of electron withdrawing and electron donating groups. Other people, specifically Taft, T-A-F-T, not related to the president, came up with what's known as steric hindrance. So if you look at the reaction up top, okay, we got an ester there, and I have an R group attached to it, okay? And what Taft was able to figure out was that the size of the group, and that's what steric means. Steric means size or bulk. So as R got bigger, as we attached bigger and bigger things where the R value is, what happened is there was a decrease in the rate of the reaction. The reaction got slower. So you see there, as R gets increasingly bigger, then I have a decrease in how fast this reaction happens. Okay, and the mechanism of that is pretty complicated. You see words there, something about a nucleophilic attack on a carbonyl carbon. We're not going to address that here, but fundamentally you need to understand that changing the size of the group, not only what group the group is, whether it's electron withdrawing or electron donating, but just the physical size of the group will influence um, how these reactions occur. Okay, so the size of R makes a difference. Okay, the Hammett equation, again, there's a lot of words here. So basically, Hammett observed that there was a relationship between some of these numbers. Okay, so he figured out there's a relationship between how fast these reactions will happen and the type of thing that he substitutes onto a benzoic acid or benzoic ester. Okay, so that's what Hammett's contribution. And he came up with a variety of types of equations. Particularly, what you're looking at there is um, he assigned something called rho, that little p-looking thing, a reaction constant, okay, to the acid ionization of benzoic acid. He basically gave that a 1. Okay, so and everything else is measured relative to that. So here's sort of a description of that. So what you see there is that the sigma value, sigma sub rho, you see there. So if I substitute an NH2 group where X should be, I get a negative value. H, look where the hydrogen is, that's the sort of the baseline. If I have an X, H where X should be, I have a Hammett constant of 0. A chlorine, the CN group, the NO2 group all give me positive values of the Hammett constant there. So you're going to, and what you should notice there is what's happening with the log of K. Okay, as I get more positive values, the log of K is going down, and that's going to change the acidity of the particular reaction. Okay, so basically what Hammett did is he came up with all of these values and published them, so what these substituents would be and how much they're worth. Okay, so he came up with what's called a sigma value, which is the electronic effect of the substituent. Negative values are electron donating. Okay, so as you see here, positive values are obviously going to be electron withdrawing. So negative sigma values are electron donating. Positive values are electron withdrawing. And if it's electron withdrawing, that basically means the drug is going to become more acidic. And you had some calculations you did last week where you looked at that a little bit. And we will continue to look at those as we go through the course. Okay, so here's some sample values that come from the literature. And again, this is what Hansch figured out is the values for all of these substituents. Okay, many other molecular properties have been incorporated into QSAR. Some of these are measurable, and I'm just going to give you a shopping list here. These are all things that we can calculate either computationally or otherwise. Okay, and here's some more. Some of these are calculated. Some of these you've seen before. Some of these you've not seen before. But basically, all of these values are things that we can either measure or we can calculate, again, which all can get included into these calculations. Okay. All right, so here's the methodology. So what you're going to do is you're going to try to find several descriptors that you either measure or calculate, okay? And then you want to do a statistical analysis, okay? And you want to try to get you want to try to find the most important 2 or 3 or 4 or 5 descriptors that are the most highly correlated, okay? So there's this is as much an art form as it is a science sometimes. Generally, as a rule of thumb, you're going to have a test set of data. You're going to have data that should have at least 5 times as many compounds as descriptors in the QSAR, and we'll give you an example of this momentarily. And the reason for that, it's complicated statistically, but too few compounds relative to the number of descriptors can sometimes give you false correlation or false results, okay? And there's all kinds of rules for how many descriptors you have to have given the size of your data set and how big your data set needs to be given the number of descriptors. We won't get too much into the nitty-gritty of some of those statistics, but just understand that I'm going to be giving you some data sets that should be pretty safe. Okay, so we'll try to keep you out of trouble. There are a number of tools you can use. We can do all kinds of there's all kinds of statistical software. Some of them are very sophisticated, like MSI Sirius 2. The academic price for this is about $20,000 for this piece of software. We don't have $20,000, so we use a free statistics package that you are coming to know and love, known as R. And for the most part, what we're trying to do in this course, R works just fine. That doesn't mean you like it, but it works just fine. Okay. Okay, so here's an example of a QSAR, and this is the lab that you're going to do this week, and this comes from the literature. So this case study looks at the anti-adrenergic activity and the physiochemical properties of a 3,4 disubstituted NN-dimethyl alpha bromophenethylamine. Wow, okay, what a name. Okay, so basically, let me say that in English. What you're going to do is you're going to take this compound and you're going to put, it's disubstituted. So you're going to put different things in for X and Y there. And we're going to give you lipophilicity data represented by the symbol pi. That's not 3.14. That's just the number we use, the symbol we use to represent lipophilicity. We're going to give you a Hammett constant, a sigma values. In this case, we put a positive on it because it's going to be for a charged cation. And we're going to give you something called Taft's steric perimeter, or E sub S, okay? We're going to give you this data, and let's take a look at it, okay? So basically what the data looks like here. Here's my test set, and this is the data you're going to be getting for the lab this week, okay? So if you notice there, I've got X in the meta position, and I've got Y in the para position, okay? So in the first example, the first drug has H in the meta position for X, and it has H in the para position for Y. And we have real data, so I have lipophilicity, I have a sigma, I have an Taft steric hindrance, and I have a log 1C observed. So this is what I call my test data set. There's 22 drugs here. And you notice as you go down, you're replacing the meta X with a fluorine, a hydrogen, chlorines, bromines. The Me there stands for methyl. We're doing the same for the para on Y. We're replacing those with different compounds. Okay, and what you're going to have to do is you're going to have to come up with a linear regression that includes your Y value here is going to be log of 1C. Your X values are going to be your lipophilicity constant, your sigma constant, and your Taft steric hindrance number. Okay, so oops, there's one more there. Okay, so you're going to want to do this. So here's an example. Okay, if I just use two of those three variables, I forget which one I used. I used the lipophilicity value, and I used the sigma Hammett constant. Okay, and notice where it says some number, and some number. It's going to be your job taking this data to figure out what each of those numbers might be. Okay, so I can do this QSAR just using two of the three variables. Okay, and the number of samples I have is 22, and when I did this, I got a correlation of about 0.95, 0.945. That's a pretty good correlation. Okay, 0.9 or better is considered satisfactory for medicinal chemistry. Okay, if I use all three variables, okay, again, now I'm using the lipophilicity or the pi value, I'm using the Hammett constant, the sigma value, and I'm using the Taft steric hindrance value, the E sub S. Okay, so I have to come up with three different numbers as my coefficients there, plus the fourth just regular coefficient. So it'll be up to you to decide for your lab if you're going to use two variables or three variables for your particular determination. Okay, same data set size there. I had N of 22, and notice I got a better correlation of 95.9% as compared to 94.5%. So by using three variables, I got a little better correlation for this particular data set. Okay, so that's going to be a Hansch QSAR, and we will demonstrate that in a little bit more detail tonight, okay, during the live session. There's also another method known as a free Wilson QSAR analysis, and in some regards, this is much, much easier to do. And well, again, we'll work on this a little bit during the mandatory Illuminate session, but I did one example here. So I pasted in the compound so you have it in front of you. But if you look at the third drug down, okay, notice in the meta position I have a hydrogen, in the para position I have a chlorine. So what I do here is I go across And so for example, look at the first column labeled meta F, okay? So the question you need to ask there is there a fluorine in the meta position? Well, the answer is no. There's a hydrogen in the meta position. So I put a 0 there, okay? Keep going across. Is there a chlorine in the meta position? No, there's a hydrogen. Is there a bromine in the meta position? No, there's a hydrogen. Is there an iodine in the meta position? No, there's a hydrogen, so on and so forth. I get over to where it says in the para position, is there a fluorine in the para position? No, so there's a 0. Now, is there a chlorine in the para position? Well, the answer is yes, so I put a 1 there. So I would do that notation, and I will show you an easy way to do this tonight using Excel. So you would fill in this entire chart with these zeros and ones, and then do a regression analysis of all of that data. And again, we'll talk about how to do that a little bit during the live class session. Okay, so that's a free Wilson QSAR analysis. Okay, so the lab for this week, I'm going to ask you to do both a Hansch and a free Wilson analysis for 22 substituted amines, basically using the data you just saw. Okay, I want you to find the log 1C regression formula for both, using both methods, and you'll need to read in your textbook to understand what a log 1C means. Okay, and I want you to find the calculated log 1C value for each of the 22 amines using both methods. Decide which one works best for the set, and we'll have to talk about what best means. Okay, and then find a set of parameters, a log P, a Hammett, and a Steric value that results in a specific log 1C value using the Hansch method. Again, if you read the lab, that will be a little bit more clear. I suspect many of you will need to attend most of the Illuminate sessions this week, not only the one tonight, but also the one on Sunday night and maybe even the one on Monday night, because you're going to need a little bit of help with this particular lab. Okay, if you have any questions, we'll see you in the Illuminate sessions. Thank you very much and have a good day.